Welcome to Data Science with EJD. Continuing from where we stopped from the last video, we continue to talk about generative unsupervised learning. Of course, that's under unsupervised learning, which is under machine learning, you know. So here in particular, we are focusing on generative adversarial networks, GANs, GANs. So straight to the point, GANs are generative adversarial networks, right, which are a class of machine learning frameworks invented by Ian Goodfellow and colleagues in 2014. They belong to unsupervised learning and are used for generating new data samples that mimic the distribution of a given training data set. So you have a given training data set, right? And then you are able to generate new data samples that look like the distribution of the data set you're given initially. That's what they are said to be generative adversarial networks. So the key idea is that a generative adversarial network has two neural networks that contest with each other in a game. You see, that's why it's adversarial. I have a playlist on game theory, in case you need to know the idea of a game in that sense. So we have the generator and the discriminator in a generative adversarial network. So the generator learns to produce fake but realistic data, while the discriminator learns to distinguish real data from fake or generated data. So you have your normal training data set, right? And then you have the generator, trying to mimic that data, whereas you need the discriminator to distinguish between the real data and the fake one that has been generated. So that's why it is adversarial in nature. So they are trained simultaneously in a minimax game. So you have minimum of the generators and the maximum of the discriminators, V of D comma G, which is equal to I think that's expectation, you know, with X following P data of X into log dx plus E Z, following PZ of Z log I minus D of G of Z, like that. So that's some serious maths there, but I mean, just an idea. So talking about generator and discriminator now, the goal of a generator is to create data similar to the training data, while the goal of the discriminator is to distinguish real data from fake. Then, talking about input, the generator, has random noise vector or latent space as inputs, while the discriminator has data sample, which is real or fake. Then for the outputs now, we have the generator. For the generator, we have fake data sample, e.g. an image, and the discriminator has probability that input is real. That's why it's a discriminator. It tells you whether what you have is either real or not. Then the objective is that the generator fools the discriminator while the discriminator correctly classifies real versus fake. So that's why it is adversarial. You can see it's a competition between generator and discriminator. Then you have type of model. So for the generator, uses a decoder-like neural network, while the discriminator uses a binary classifier. So that's what a generative adversarial network looks like. A fight, a competition, a game between generators and discriminators. Then when we talk about DCGAN, that's deep convolutional uh, generative adversarial network. This again is an extension of GANs that uses convolutional neural network, CNNs, for both generators and discriminators, right? This makes generative adversarial networks effective for image generation. So DC GANs are stable and produce better image samples than fully connected GANs, right? So key features of DC GAN they use convolutional layers instead of fully connected layers. They replace pooling layers with strided convolutions, and they use batch normalization. They use RELU activation in the generator, except for output, which often uses tanh, and then they use leaky RELU in the discriminator. Common examples, you have the generating handwritten digits. So we've done something with the handwritten digits thing before. Then they also you also have the generating human faces. You're talking about celeb A. Then you have art or anime synthesis. So let's do a Python implementation example of all this. So let's implement a sample DC GAN to generate MNIST handwritten digits. So first of all, you need PyTorch, right? Python DCGAN example, DCGAN example with PyTorch. So first of all, you want to install the dependencies. Of course, as usual, it's always nice to see the line numbers for easier referencing. So here, you install Torch Vision. Of course, if it's your first time, but if you already had it installed, you can move to B. But I'm just doing this for the sake of it. But I mean, requirements already satisfied because I've installed all those before. Then the next thing, you import the necessary libraries. Torch.nn, that's neural network. Now Torch.optim, more like some optimization thing. Torch Vision, import datasets, transforms, and all this, right? So don't forget to run. So I mean, this task shows it's running. So when it's fully run, then you have a number showing right there. Two now done. Then we can go for the hyperparameters. This is where we tune things. So we talk about the device, touch device, CUDA. If touch.CUDA is available, else you use CPU. That's talking about the machine you're using. Then talking about hyperparameters. Now you have bat size of 128, image size of 64, NZ, that's latent vector size of 100, NDF, that's generator feature maps of 64, NDF discriminator feature maps of 64 again. Number of epochs is 5, and then LR is 0.002, and beta 1 is 0.5. So we run that, and that is done. So the next thing is you can load the data set, right? So for the transformer, you have so for the transform, you have transforms.compose, transforms.resize image size, transforms dot to tensor size, transforms normalize 0.5, 0.5. You now have the data sets to be all this now, and data loader is all. So you have data loader is taking data set, batch size, shuffle, and all that. So we can run and also try to visualize. Let's see if this can give us a picture of what's going on right there. Okay. Okay, that's done. Nothing special to see. What if I change it to data sets though? Data sets. Does it show any? Okay, just tells me some things about the data itself. Number of data points, 60,000, that's a lot. Root location is the data, split is strain, standard transform, and all that. So those are the kind of things we get to see with that. Okay. So we have all that. Then you can now create the generator here. We're talking about generator and discriminator. So for the generator, now you use object-oriented programming. So we create a class called generator with neural network modules, and then you have some functions to initialize. You have a super thing going on here with the initialization. Then you do all the whole transposing, batch norm, ReLU, all those things we've talked about, and then you define forward and all that. So just run that, and that's easily done. And then after creating the generator, you also create the discriminators in like fashion, something like what we just did with the generators. So same for the discriminators now. So that's also done easily. And then we initialize the models. So net G is generator to device, net D is discriminator to device. Then initialize the weights and all that. So we run this. Okay. So it gives us some of this information, conf 2D, blah, blah, blah. It gives us all this info. And then we have the loss and optimizers now. We have this pretty easily. Then the training loop, this is where the issue is. Now, this may take a lot of time to work. So we may even I'll just continue because I know it's going to take a lot of time. Yeah, so we have 5 epochs. So it's epoch 0.5, and step is 0 out of 469. The loss in the beginning is 1.7124. Loss in the discriminator is 1.7124. Loss in the generator is 4.9788. So as the epochs advance and the steps advance also, for each epoch, you're going to have a number of steps. And as that happens, you're going to keep having, the loss values will keep reducing as expected. So to make the system as efficient as it should be. But I mean, this can take some hours, so I will just go on because this is still running. If I try to do this, we won't get any result from it, but I can just move on. So we'll keep revisiting. We'll see how far it goes before by the time we are rounding this off. So the data set here is this. We have the MNIST data set, and then we are using touch vision.dataset MNIST for easy loading. For more realistic images, we can switch to data set like Celeb A, which is talking about faces of celebrities, I believe. And you have the cipher-10, which is for natural objects. Okay, you can see it is still, running it is still on the 0th step of the 0th epoch out of 5, right? And in summary, you have GANs, which learn to generate new data via adversarial training, uh, you know, and did see GANs, improve GANs for image generation using convolutional neural networks. Then Python and PyTorch make it practical to experiment. I mean, we are still on that since, right? So uh, let's see how far this goes. While I try to sign out, well, we can say this is the end of this video. Of course, this is still running, and we are not able to visualize anything yet. Let's see if, of course, I can guarantee that this can continue for the next 1 hour or two or something like that. Because once we begin to, talk about neural networks, things become really complicated, and you need some serious compute time, or maybe like you need a faster machine if you want faster results. All right, so let's take it that we've come to the end of this video. Feel free to let me know how helpful this video is for you, and if there's something you'd like me to try out, feel free to also tell me. If you have subscribed already, thank you so much. I think we need just 3 subscribers to hit 1,000. So you definitely want to make that happen. So please go ahead and subscribe, and don't forget to hit the notification bell so you can always get alerted each time a new video is released. Then on my channel, you can become a member with different levels of benefits. So just click on join and see where you want to belong based on the kind of perks you really would like to enjoy on this channel. And of course, if all you do is subscribe, of course, you still have these videos coming, so not to worry. So I mean, but if you become a member, you can have some special privileges for sure. All right, so be sure to subscribe and join if you can. Then always like and share so that more people can have access to this content I have here. Remember that you have access to my code sheets and all data sets, if any. You can access that through my through the link to Google Drive on YouTube, in the description box on YouTube and on Facebook also. So I always advise you download these things, and you you walk along, you code along, or I mean you have all these codes already in the sheets, right? So you can, if you see a number, you can tweak to know what those numbers are really doing in those places. So you can see this is taking a whole lot of time. We are still on the first. Yeah, thankfully. Now you can see the loss in D is now 0.0664, and the one in G has also gone down a bit to 4.9317. So I think it jumped to like the 100th step of 469. I don't think we want to wait for this. But of course, by the time it's all done, then you can then visualize and see what happens. So let me bring this to a close at this point. Till I come your way again. Keep doing data right. Bye.